Thank you for the invitation. So can you see my screen now?
Yes.
Okay, and now it should be full screen.
Yeah.
All right. Yes, thanks. It's a pleasure to talk at the Tata Institute virtually. I'm going to talk about a relatively straightforward question, which is the following: whether if we want to imagine that we have a theory with a de Sitter false vacuum, and there is a true vacuum which is Minkowski or ADS. And we want to ask the question of whether it is possible to uptunnel and produce a big enough bubble of false vacuum that can inflate. So that's basically the question that I want to ask in this talk, and it's based on this paper. So first we should ask this question in general QFT. We want to ask it eventually, of course, in the presence of gravity. We want the theta and inflation, but let's first ask it in quantum field theory. In quantum field theory, what happens is that if I have this double well potential, then I can always produce large bubbles of false vacuum by spending enough time and energy. So for instance, one possible scenario or one possible recipe to produce a big bubble of false vacuum is to start from a state that has a big bubble of false vacuum. And this is guaranteed to decay into the asymptotic states of the true vacuum. So now if I apply time reversal to this asymptotic states, I produce this, this bubble of false vacuum. Okay, so in quantum field theory, it is possible to explore false vacuum. And if the decay rate is small, then we can produce very big regions of false vacuum. However, they are guaranteed to decay back as indicated here. So we will always go to the asymptotic states of the true vacuum, and of course we will have asymptotic Minkowski. And what happens is that the story is qualitatively different when we go to the gravitational case, because if we produce a big enough bubble of false vacuum, then it can inflate. And in fact, that's the regime that we are interested in producing an inflating bubble. And then if we get such a situation, then we will change the asymptotic structure of the spacetime. So here I am showing the Penrose diagram of a setup that was considered by Garriga, Vilenkin, and Zhang. This is a setup that, this is a Penrose diagram that arises after inflation in this paper, but I'm just stealing the future part of that diagram to just show what is the structure of the causal structure of the spacetime. So as we see here, we have the asymptotic Minkowski part and asymptotic the Sitter part of the spacetime. So this the future asymptotics have changed, and there is a Penrose singularity theorem that tells us classically this spacetime should have a singularity in the past. So it cannot arise from just Minkowski space in the past. And indeed, in this paper, it didn't arise from Minkowski. It was coming from inflation. So we want to ask whether it is possible to have this via a quantum mechanical tunneling process. And this is a question that was asked 30 years ago. So it's an old question by Farhi et al. And Fischler et al.
Sorry, Mehrdad,
Yes.
about your previous Penrose diagram. So I should look at this as like an inflating bubble happening behind the event horizon of a black hole?
Yes, yes.
Okay, thank you.
Later, I think I will have another, some spatial section of this diagram. So there will be some wormhole that connects me to the inflating reach.
I see. And here you say you can set up some initial conditions that would give you the solution.
Yeah, so you can imagine some inflationary scenario that has, for instance, there is some slow roll valley and some other vacuum, and you can tunnel to that other vacuum during inflation, but then the slow roll valley goes down, so you reheat and get FRW, but some part of the universe gets stuck in that false vacuum. So that was the story in this paper.
Yeah, thank you. And from the point of view of the outside, this would be one of these primordial black holes?
Yes.
Okay, thank you.
Sure. Of course, everyone, please ask questions if there is any subtlety or any point. Okay, so yes, we want to ask this question. Or ask whether this can happen quantum mechanically. And this question was asked 30 years ago by these authors. So basically they asked the following question. They considered tunneling from Schwarzschild spacetime to the zeta, so the starting point is Schwarzschild, and then the end point will be Schwarzschild plus a bubble of the zeta. So in fact, sorry, so it's not exactly Schwarzschild, it is asymptotically Schwarzschild. And what they consider is that they consider a situation in which they start from a small bubble of the zeta, so this is this part. And that a small bubble of the zeta that will not inflate, is too small to inflate. That is tunneling to a big bubble that is going to inflate. So that's the setup that was considered in that paper. And again, I'm going to talk a little bit more about this. But before talking about this model and about what I'm going to do, let's just say a few words about motivations of why we are considering this problem. Why are we asking this question? So there are a bunch of motivations. First of all, this seems to be a well-defined question, which is relatively rare when we talk about quantum gravity in the zeta. Just out of curiosity, it seems that we should be able to answer whether it's a possibility or not. And especially if it's, for instance, the answer is no, it will be a particular feature of gravity, something that would be allowed in quantum field theory is not forbidden in gravity, meaning that something being exploring big regions or producing big regions of false vacuum. The question is also kind of subtle because, first of all, because it hasn't been settled in after 30 years. So there has been those works, but until today there seems to be no consensus whether the solution that was found there is an acceptable solution. So there are discussions on that. And also because when we get this configuration, we have a bubble of the zeta, which is behind the black hole horizon. And the zeta entropy will be larger than black hole entropy. And this sounds a little bit puzzling. It's not obviously a contradiction, but it's something that can stimulate maybe more interesting questions, especially now that we have better understanding of black hole entropy. And then if we can embed this bubble of the theta in some asymptotically ADS or Minkowski space, and then we might be able to use holography or or what we understand from gravitational S matrix to learn something about observables in this theta. So it might be useful.
So
because
Mehrdad,
there is a question of dictionary. Yes, sir.
Why is it not a contradiction if the de Sitter entropy is greater than the black hole entropy? For instance, if it was embedded in an ADS space and inside some field theory.
Well, because I guess at least I do not fully understand what the theta entropy means. I mean, it's an area. When I say the theta entropy, I just mean the area, right? The horizon area divided by 4G Newton. But I'm not really sure what it is counting. And I should say there are similar situations, not just DS. For instance, I think people consider bags of gold geometry it seems that they can also have bigger entropy than black hole entropy. Yeah, I would say that once one understands what the theta entropy means, then there can be sharp questions.
Thank you.
Yeah, can I ask you a question, Mehrdad?
Yes.
So you say that the radius of the de Sitter is bigger than the Schwarzschild radius. And so maybe I am not getting the geometry all right. So the DS bubble will hide behind the black hole horizon.
Yes.
Its radius bigger than the Schwarzschild radius.
Yeah, I have a picture. Maybe I can go forward a bit to show this picture. I have a picture of the spatial cut of the geometry. Or I mean, this is a spatial cut of this geometry. So you have asymptotic Minkowski. So imagine this is a slice through this geometry. Say it goes like this. You have asymptotic Minkowski goes through the black hole. So there's black hole horizon. It goes through the wormhole and then opens up again. And then eventually the sphere, the transverse sphere closes at this point. So this is the R equal to 0 point.
I see. And presumably this does not violate the Bekenstein bound. Is that right? I mean,
sorry, say it again. I didn't follow.
So something with a larger entropy than the black hole itself is behind the Bekenstein, behind the Schwarzschild horizon. So it
right. So in fact, it's behind the other. You have both horizons of the Schwarz. Yeah, and then behind you have some geometry, some de Sitter geometry with bigger.
So I guess it avoids violating the Bekenstein bound because it's on the other side.
Why is it not? Well, again, my answer is the same as before. I can formally calculate something called the Sitter entropy by dividing the area of horizon by 4G Newton. I'm not sure what exactly it means.
Okay.
Yeah, I have a question actually. So
yes.
Following, is this Bekenstein bound actually valid for a time-dependent situation, or it's for equilibrium situations?
I guess I'm not an expert. I don't know.
It was a question for everybody. I mean, I am not an expert either.
The Busso version of it, based on light sheet entropies and so on. So maybe that is not applicable here, perhaps.
I guess that one will calculate the flux of entropy. If I remember correctly, it calculates the flux of entropy between 2 points, and then talks about the change of area. But I might be mistaken with some other bound. while here, again, I guess I'm not sure how to calculate the flux or how to associate the de Sitter entropy to, for instance, some flux of entropy that I can associate to the matter field.
Okay, thank you.
Maybe I can make a comment here.
Yes, yes, please.
Cassini showed, Horacio Cassini showed that Bekenstein bound is really, when written, interpreted properly, is equivalent to the statement that relative entropy is a positive quantity, and therefore between any two states is always positive. So whether it's time dependent or time independent wouldn't matter. Its precise version of the Bekenstein bound, which is the positivity of relative entropy, is valid. So it would be true for dynamical situations as well.
Okay, I see. Okay, thank you.
Thank you. I guess I'm not claiming that this is a sharp puzzle or contradiction, but it seems to be thought-provoking at least, and that was one of the.
Could I ask, from the point of view of the outside, does the black hole eventually Hawk? Can you set up a situation where the black hole eventually Hawking radiates and disappears?
Yes, yes. I would say generically it will.
And then what happens to this inflating bubble part? It's sort of just after
well, and from the inflate, so let me for a moment. So here, for instance, so I guess one simpler scenario would be, I mean, the easier case to consider would be to have Schwarzschild connecting directly to the theta. Here, there is also a flat region here, and there is a domain bar.
Right.
So what happens, I think, is the usual thing, meaning that this black hole evaporates in this flat region on both sides, but the theta part doesn't care about it.
So the end result of the space-time at the end, once the black hole is completely gone, is what? On the right-hand side, there's just flat space, right, or whatever.
Yes.
And on then there's a bubble of de Sitter also, a separate bubble of de Sitter.
Yeah, this part should be yeah, on the left part. I think I should have just a closed universe. Yeah, but then I guess the question is that, yeah, I'm not 100% sure how the dynamics of this domain is gonna work, because this is the eternal geometry. But if I disconnect, if the black hole completely evaporates, then I should get a closed geometry here.
Right. So it's like now what you started with some flat space kind of thing, and now you've got flat space plus a disconnected bubble.
Yes. Yes.
Okay. Thank you.
Sure. Yeah. I guess I'm not exactly sure how this disconnected bubble is gonna look like. Because this is not exactly the setup that I'm gonna consider. But if you imagine the black hole lives inside the theta, so you have on the other side of the black. So this is on one side is the Schwarzschild de Sitter black hole. If that is the case, then what would happen is that the black hole would the Schwarzschild de Sitter black hole would evaporate on one side, and on the other side, the Schwarzschild black hole evaporates, and you just get the theta on one side and flat on the other. But here, I guess one should also talk about what happens to this domain and the flat region that is separating. that I need to think a bit about. Okay, so let me go back to the motivation.
Mehrdad?
Yes?
Yeah. Sorry, I have a very basic question. In the
Yes?
beginning, you talked about the qualitative difference between quantum field theory and quantum gravity.
Yes?
In that, in one case, it will degenerate, decay, and the other case could expand. So,
Uh-huh.
at the basic level, why is that? Why is there such a difference?
Well, in quantum field theory, it's just the fact that this is a false vacuum. So everything, eventually I will have, I mean, quantum field theory, I mean, Minkowski spacetime. I do a scattering process, eventually everything goes to the asymptotic states of my theory. And a configuration, a bubble of this, bubble of the city is like a non-stable state. So that is not an asymptotic state. So eventually.
Yeah, so this I understand, but in gravity, why this sort of explanation is not?
Oh, because in gravity, if this bubble of false vacuum is very big, then it will inflate. Imagine if the size of this bubble is larger than one curvature radius, then it inflates. And then you have, in principle, down tunneling, the usual Coleman-DeLuca down tunneling from the inflating region back to the flat region, but that down tunneling can be exponentially suppressed. Therefore, it's generically, I mean, it depends on the parameters of the potential, but for some range of the parameters, you will get eternal inflation if you produce this big bubble.
Okay, so this expansion process is not quite a tunneling process, is it? It's just a dynamical process that.
Yeah, it's just the usual, the same thing that we have for inflation. The same thing that happens now today is just the normal expansion of this this region which is in the false vacuum. The exponential expansion that I get here.
Okay, thank you.
Yeah, that's the classical. That's just the classical evolution of the bubble, which is something intrinsically gravitational. It's not present in the field theory. The field theory wouldn't care about the vacuum energy. Gravity cares about the vacuum energy. If it is positive, then it expands. Okay. So yes, so I talked about these motivations now, but I guess for me, maybe the main motivation is that this is a setup that allows us to, helps us to wonder about the origin of our cosmology or universe. So I want to make this analogy with the theory of inflation, which was a theory for the initial condition of the Big Bang, hot Big Bang cosmology. So asking about what happened before the hot Big Bang led us to finding this nice, simple theory that can explain lots of observations. And of course, in principle, one could say that, oh, at the hot Big Bang, there can be some Planckian physics that determines the initial condition of the universe. But insisting that we want to get some semi-classical description for this initial condition was useful there. Now we know that the inflation itself is not past complete. By the same Penrose singularity theorem that I mentioned, there has to be a singularity to the past of inflation. And again, the conventional wisdom is that there should be some Planckian physics. Quantum gravity has to determine what is this initial the initial state of the universe. But we could ask, could there be some semi-classical description that gives us the wave function of the universe? And in fact, again, this question was asked more than 30 years ago by many people, but including, and probably most famously, by Hartle and Hawking, who proposed a no-boundary solution. So this no-boundary solution is indeed a semi-classical origin for the wave function of the universe, or for the inflation. And the idea is that, so this is supposed to be an inflating universe. I'm imagining inflation in global slicing is the hyperbolic space. And then the idea of Hartle and Hawking is that the state is produced by some Euclidean evolution that has no other boundaries. So which means that now I cap off this Lorentzian geometry by a hemisphere. And this is a successful prescription for the fluctuations, for the wave function of the fluctuations during inflation, but it also has some drawbacks, or at least one obvious drawback, which is that if I ask about the scale of inflation that I get, given some potential for a scalar field, then the Hartle-Hawking proposal predicts the lowest value of the potential to be the most probable point to nucleate this universe. So therefore, since it gives highest probability, exponential higher probability to the bottom of the potential, say here, for instance, or here, then it means that no inflation will happen, or it predicts zero amount of inflation. So now one could wonder if there can be a different semi-classical origin, which is the following. Can there be a semi-classical scenario, which is that there was an eternal Minkowski space to the past, and at some point there was a uptunneling to some quasi the theta region, or to a higher point in the potential, and we had this inflation for a while, and then it reheats and it produces our universe. So this is perhaps the more cosmological motivation for asking this question. All right, so now we already talked a bit about the existing examples. There's one by, or at least the ones that I'm aware of. There is this example by this author, by Garrigo, Vilenki, and Zhang, which has some of the features. For instance, it does produce a universe with or a space-time with an inflating bubble connected to asymptotic Minkowski. So therefore, some of the questions, like for instance, this question about entropy, can already be asked in this setup. But some other questions are not answered by this scenario, because in the past, in this scenario, there is inflation, or not Minkowski space. So it starts from inflation, and one might like to get inflation by starting from Minkowski or ADS. And then the other example, again, I mentioned it, is the scenario by Farhi et al. And Fischler et al. And so this is the space-time diagram at the of the initial conditions before the tunneling and after tunneling. Both of them are then analytically extended. So the idea of this paper is to consider a bubble of the theta that is small, and therefore it just collapses, and we get just a Schwarzschild geometry. and ask if we can have a tunnel into a bubble of de Sitter which is big and it can inflate. So tunneling from the left to the right. They don't talk about how to produce, or it's not that, it seems that it's not a serious obstacle to produce this picture on the left, to produce a small bubble of de Sitter, because we know that in quantum field theory we can produce bubbles in the false vacuum. So a small bubble of de Sitter is like a bubble that we produce macroscopically in the lab at the scales in which gravity was not important. And then we know that it collapses. Now, the problem is that the reason why I'm giving this talk is that this solution is not, the solution that these authors found is, it has some singularity. So they find some Euclidean Euclidean solution that interpolates between these two geometries, or to be more accurate, interpolates between the spatial slice of this geometry and the spatial slice of this geometry at the moment of time symmetry. So that's basically the rule of semi-classical gravity to calculate probabilities. We look for Euclidean geometry that allows us to, or transition amplitudes. So the Euclidean geometry is giving us the semi-classical, this prediction for this transition amplitude. However, this Euclidean geometry that they find, it has a singularity, and it's not totally clear if it is an acceptable instant, acceptable solution that should be allowed in the quantum gravity path integral. And there has been discussions on this until recently. So these are two recent papers that have opposing ideas on whether or not we should accept this scenario. So one way is to think more about the nature of this singularity and trying to resolve it. I think another route would be to try to find other alternative solutions that don't have that singularity. In fact, at least if we find those, then I guess that basically answers the questions in a simpler way. And that is what I'm trying to do here in this talk. I'm going to propose an alternative scenario. So now this alternative scenario is essentially related to a question that was formulated in this paper by Fu and Maroth, which is a similar question. Is that whether I can produce via Euclidean path integral some state that is asymptotically ADS, but it has an inflating bubble inside. And then they conclude that the answer is negative or the answer is negative unless you allow geometries that have the same issues as the geometries that I mentioned before. So unless you allow these singular geometries, it won't be possible to do that. And the reason is not too complicated. It's basically how the transverse direction is expanding in ADS and in de Sitter. That doesn't allow to have a positive tension domain wall between them with the requirements that we want. Now, why is this question similar? It's similar because, first of all, we want to produce this state, but we know that Euclidean path integral is a way to produce a state. So this preparation via Euclidean path integral is seems to be a way to imagine how the scattering states would produce that. And also, if we do it in ADS, then we can take the flat space limit, and it's likely that also it is also possible in flat space.
Sorry, by Euclidean path integral, you mean with operator insertions?
Well, they do not have any operator insertions. They are just working in the thin wall approximation. So these are the ingredients that they have. Only a thin wall and then 2 vacua.
Sorry, I suppose I'm not understanding what you mean by Euclidean path integral. Do you mean that it's an infinite, like starting with the, yeah, please explain what you mean by Euclidean path integral, please. Okay, so what I mean is I want to find a Euclidean geometry that contains, which is asymptotically ADS. So this is the disk, for instance. R equals to infinity is the boundary of ADS. Yes. So I want to find a Euclidean geometry that is asymptotically ADS, and then it contains inside there is a domain wall, and across the domain wall I have asymptotically, not asymptotic, I have the region of the theta. So the transverse direction, so this is R equals infinity at the boundary here, that's the boundary of ADS, and on the left. And then on the right, I have a region of the theta, and this is R equal to 0 when the radius of the transverse direction shrinks to 0. So I want to glue a patch of the theta to asymptotically ADS spacetime such that I satisfy a junction condition. I have a thin wall with the positive tension. And that's basically the question. Can I find such a solution? Why is it, okay. So yeah, why is it interesting? Because then if I get this solution, if I cut it at the moment of time symmetry, then it's gonna generate for me what I want. So the physical interpretation of such a solution would be tunneling from the vacuum of the field theory into the state, right? They are considering, they are allowing mass Schwarzschild ADS. So they're allowing, sorry, what? Massive? Schwarzschild ADS. So they can be excited, not like, in fact, if that, we don't expect to be able to tunnel from a vacuum ADS to Minkowski. There should be, we should excite the vacuum to be able to do that. Right. So, and you're exciting it with an ensemble. But I was wondering if, is that right? But I was wondering if you could excite it in a more intricate way by putting operator insertions on the Euclidean path integral. But that's exactly what I'm going to do. But that's what you're going to do. I see. Thank you. Yes. Yeah, but for some reason, this is just what they consider. This is the setup that they considered in this paper. And I think that basically the reason or the way to go around this no-go theorem is to consider these local operator insertions. There is and then I think there is, I guess there is some geometric reason why it helps with the situation. Okay, but so before going that, let me just mention one other thing, which is that so these are some reasons why in general solving this problem in ADS is related to asking this question in asymptotic or Minkowski, although answering it in ADS by itself I think it would be interesting enough. Doesn't have to be Minkowski, but they are related. But there is a closer connection if we consider the near horizon geometries of near-extremal black holes. And this is a subject that recently there has been a lot of work on it. I have only listed some of the authors. I'm assuming some of the authors probably are in the audience, and I have probably forgot to write them. There is a long list here. So what is the idea? The idea is that we want to focus on a spherical symmetry just for simplicity. And we want to consider black hole solutions with these ansatz.
So we consider two solutions. One is Schwarzschild de Sitter solution in the false vacuum. This is the Penrose diagram for this Schwarzschild de Sitter solution. The spatial topology is R times S2 if we are in 4 dimensions. We can be in higher dimensions. This S2 becomes SD minus 2 in higher dimensions. So what we have is the spatial topology here is R times S2, and then this function f is given by this expression. In particular, it has the property that this function has 2 zeros, which give, or more than 2 zeros, but 2 positive zeros that give you give the location of the horizons. And when the two roots of this f coincide, then we have the extremal solution. Similarly, in the true vacuum, we can consider charged black hole, Reissner-Nordström black hole, with this Penrose diagram. I'm considering a maximally extended solution, or a two-sided solution, with these two sides 3 and 3 prime identify with each other. So I have a spatial and non-trivial topology. Again, there are two solutions, outer horizon and inner horizon. And when the two roots coincide, then, or become close to each other, we become near-extremality. When they coincide, we have extremal geometry. So if I want to show if we want to see the spatial geometry, it looks like this. This is the drawing by Wheeler of a wormhole. So this is supposed to describe the Reissner-Nordström wormhole that we consider in the true vacuum. So these are the two. So this picture is supposed to be one special the slice of the geometry, keeping in mind that these two asymptotics are identified. So this outside region. And what happens is that if we go near the extremality, the length of this wormhole becomes longer and longer. On the Schwarzschild, on the de Sitter side, or Schwarzschild de Sitter side, we have this geometry with the topology of R times S2, and the idea is to the proposal is gonna be to nucleate a bubble to produce a region of this Schwarzschild de Sitter geometry in the middle of this wormhole. And why is it? Why do we consider this contrived setup? Because the reason is that it's when we go near the extremality, the problem simplifies, because the size of this wormhole, the transverse dimension of this, or the transverse size of the wormhole, which is size of the S2, becomes approximately constant, so we can do dimensional reduction to 2D. So that's basically the reason. It simplifies the calculation. So we can we basically get this effective 2D theory with where the relevant geometric degrees of freedom is the two-dimensional part of the metric G mu nu, and phi is the deviation of the size of the sphere from whatever the extremal value. So this phi is a small value, and it is called dilaton. And the model that I get in 2 dimensions, this effective model that we get is Jackiff-Teitelbaum gravity coupled to the matter. So we have reduced the Uptunneling problem in Minkowski, or asymptotic Minkowski, to an Uptunneling problem in asymptotically ADS. Oh, I guess I forgot to say the ADS part. So this near horizon geometry of the Reissner-Nordström wormhole is ADS2 times S2. So this G mu nu in the true vacuum will be close to ADS2, And then the G mu nu, the 2D part of the metric, will be in the false vacuum will be close to ds2. So if we go back to this picture, if we focus inside the wormhole, in this region we have basically a ds2 times s2, and in this region we have ds2 times s2. And the size of s2 is approximately constant, or it changes, it has a small variation from its extremal value, and that extremal variation is called the dilaton. Okay, so then, what we want to ask is basically the same thing. We want to calculate some transition amplitude using semi-classical gravity, which means that we want to calculate some Euclidean bound solution that can be cut in the middle and be Wick rotated into a geometry that gives us this expanding bubble. So this is the formulation of the problem that we want to consider. Now it has reduced to the two-dimensional problem, and we want to consider the Euclidean geometry. So the Euclidean de Sitter, Euclidean ADS, I have written it here, is a disk topologically. And then there is a phi solution, a dilaton solution. And this constants basically determine, this A determines how close I am to extremality. So if I set A to 0, then I have an extremal solution. Similarly, here I have ds2 in Euclidean signature, which becomes just a two sphere. And again, the phi solution, which is the deviation of the transverse direction. B again determines the deviation from extremality. And this P0 is an offset between extremal size of the Reissner-Nordström and the extremal size of the Schwarzschild C. So these are three parameters of the model. And then in addition to that, as Shiraz anticipated, I'm going to put some extra object in here. I'm putting the brain in here. That is something that we can imagine we produce it by putting some sources, some boundary sources in this ADS solution. So originally we would have the ADS disk. Now when I put this source, what it does is that it effectively produces some extra space between the horizon of the black hole. So if we go here to the Lorentzian spacetime, this putting this brain in the middle produces some extra space, and basically that extra space, it allows us to nucleate a bubble of the zeta in the middle. Without that, it wouldn't be possible. And so we have this brain, and then the question is, can this brain bifurcate, decay into the domain walls of the de Sitter region, and such that those domain walls, if I cut them and analytically continue them, they fall into the black hole horizon. Therefore, they leave here some region, some expanding region of de Sitter. So these are the ingredients. The ingredients are these, basically the parameters that determine how close I am to the extremality of these black holes, and then the tension of these domain walls. And this is, yes.
Could I understand this domain wall? Is the idea that there's some potential and the domain wall is the interpolating region between one vacuum and the other? Is that what?
Yes. Exactly. Except that I'm just working the thin wall approximation. I'm just considering it as some some microscopic object that exists.
But the cosmological constant is different on the two sides of the domain wall.
Yes, yes.
Okay. And so in a more complete treatment, you would have to have the scalar field whose potential you have this domain wall, but that is not there in your problem.
Exactly. Yeah, there is some scalar field that here along this green lines is interpolating between the two minima. So if you like, if you consider this configuration in the middle, this is like having a king anti-king configuration, which I have just approximated the boundaries by just two delta function sources.
Thank you.
Sure. And yes, then yeah, the important thing is that now let's, if we look at the Lorentzian the Penrose diagram, so what we have is that this diagram is just a diagram that shows the Reissner-Nordström wormhole. So these two sides, these two lines, are the ADS2 boundaries, UV boundaries of ADS2, which should be identified with these two modes of the wormhole. So this is just a spatial section, but if we consider their trajectory in time, then there will be those two lines cross this two factor, which is suppressed in this diagram. So these are the mouths of the wormhole, and then there is this excitation in the middle that elongates the wormhole. And then what happens is that we are now having this region of the false vacuum in which nucleated inside this wormhole. So inside we have the seater, here there is the seater, and on these two sides we have the ADS region or ADS black hole region. This so here is Schwarzschild de Sitter, and what we want is that the domain was falling to the Schwarzschild singularities, and we get the de Sitter asymptotics, a piece of the de Sitter asymptotic. Now, this setup is in this approximation of when we are in the near horizon geometry and we are two-dimensional. However, near here, I'm eventually going to get a full higher dimensional inflation. So eventually the size of the sphere expands here, and then it becomes just a normal inflation. So if this works, this accomplishes what we want in 4 or higher dimensions, because we are going to get this inflation in this region. Okay, so now basically the only question that you need to answer is to determine the motion of these domain walls, which are fixed by some junction conditions. So we need some continuity of phi, basically the size of the transverse direction, the size of the sphere has to be continuous, and then there's a discontinuity in the extrinsic curvature or the normal derivative of this phi. So these are the equations that govern the motion of these domain walls and branes. They have some consequences. It doesn't, well, there are some details. One thing that I can mention is that I draw this picture, this weird picture here, instead of just drawing a bubble in the middle of ADS. And the reason is that you cannot just carve a bubble of the seater inside the ADS. There has to be some conical singularity if we were to extend the ADS part beyond the domain wall. Of course, we are not extending it, so there's no singularity in reality, but that's why this picture looks like this. So these dashed lines have to be identified with the solid lines here. All right, so yeah, so then it's just trying to apply these equations to the motion of those domain walls and branes. For instance, we apply to the brain, this brain in ADS is something that has been considered relatively recently by Korkolo and Maldasenna. You might have heard about it for because other motivations. So this is usually called the end of the world brain. Here is different than their setup because now we are not identifying the two sides. They are identifying the two sides of this brain, and then it becomes the end of the world. Here it's just a brain inside the ADS. It moves along the geodesic.
Sorry, so this brain, because we're in ADS2, is just like a particle world line?
Yes, it's just a particle.
Okay, so it's just a source of energy, basically.
Yes. Of course, in higher dimension, I mean, we have done a 2D reduction. So in reality, it is a codimension one brain, the spherically symmetric codimension one brain.
Okay. Yes. Thank you. And could I ask Mehrdad, is the intuition that if you inject some localized energy, it makes it easier to go over the top in that localized region? Is that one way of thinking of it?
I haven't thought about it this way, but I guess one point is that going above or producing the bubble itself, it might not necessarily be the hard thing, because we know that in QFT we can do it. It seems that somehow gravity doesn't allow it, but yeah, the way I thought about it was that this allows the geometry. Basically produces some kind of kink in the geometry, and that kink allows me to put a bubble of the sitter there. While if I didn't have this brain, there wouldn't be any kink, so the size of the transverse dimension would just shrink and then would expand. But no, maybe that's the.
No, I'm not sure at all. But thank you very much. Yes.
Okay, so the next thing to think about is that the bifurcation of this brain or this particle into the domain walls. This is a microscopic process. So there is some energy momentum conservation that essentially determines this angle here. The only thing that the only geometric aspects of this picture is that the sum of angles should be 2 pi, so there is no conical singularity here. And then the ratio of the tensions will determine this angle, which is related to the initial condition or initial velocity for the motion of the domain. Now, let me just mention some possible. Well, I mean, in this scenario, I'm not talking much about the details or macroscopics of these domain walls and brains or particles. And the reason is that we want to understand if gravity allows this process to happen or not. And since it happens in QFT, it seems that if it allows it in this toy phenomenological model, it's probably a possibility. But let me just mention one possible microphysics for this decay. So we were considering this double well potential. Let's go to the 2 dimension. So again, 2 dimension, we have some field with the potential which has 2 minima. Now, if this minima were degenerate, then we would have kink anti-kink configuration in the model. Now, if it is not degenerate, we still have them have this configuration as some metastable configuration. So this is something that I'm drawing here. And then we have the fundamental particle in the true vacuum. And there is a coupling between the fundamental particle and the kink-anti-kink configuration. However, if we are at weak coupling, there cannot be any decay. At weak coupling, the mass of the kink-anti-kink configuration is much larger than the mass of the fundamental particle. So there won't be, the decay is forbidden in Lorentzian signature. However, this means, or kinematically it is forbidden, but this actually means that it is allowed in Euclidean signature. So it basically looks like the diagram that I showed here. A forbidden decay in Lorentzian signature. Looks like this, allowed decay in the Euclidean. Now, what the novelty of this setup is that we are basically saying when we embed it in gravity, gravity allows us to, this domain was to eventually be weak rotated to Lorentzian signature. So the analogy would be, for instance, considering some light axion field that is coupled to electrons, but the process of axion decaying to E plus E minus is kinematically forbidden because the mass of axion is much less than mass of the electron. Now, if we consider having a strong electric field, then the electric field allows this forbidden decay to happen. So here, what we are saying is that the gravitational field allows the forbidden decay to happen. All right, so then finally, once the decay happens, we want to follow the motion of the domain was it has, it's equivalent to the motion of a single particle in a potential. This is the effective potential. It just depends, the details is not important. I just want to show that it depends on the parameters, some combination of the parameters of the problem that I mentioned before. And for some choices of the parameters, this potential has some allowed region. So we have this, this motion with zero energy. So allowed region in this Euclidean setup would be the negative part of the potential. So this particle can move back and forth in this potential. These are the turning points. And the turning points are the points where I would be able to do a weak rotation to the Lorentzian signature. If I now in the Lorentzian signature, I will have the same similar problem, except that the effective potential is minus V. So for instance, if I weak rotate at this point, at this larger turning point, the domain is guaranteed to just follow towards theta equals pi, which in my convention is the black hole horizon. So if I get a solution and I have the moment of time symmetry to be this turning point, then that would accomplish what we are interested in. And that solution exists. There is one condition to satisfy, which is that we don't want to have a conical singularity inside the de Sitter bubble, and that puts a constraint on the parameters of the mod. So there exists a solution, and given this solution, we can also ask about the action to estimate the probabilities. So we can do a saddle point approximation and ask what is the probability of having this de Sitter region versus just a brane. And then using that JT gravity action, some regularization, what we get is that the difference between the bounce action and the brane action would be something about the phi times the area, or phi times the Bekenstein-Hawking entropy of the black hole, which implies that if I calculate this ratio of probabilities using this semi-classical formula, I get something that is much larger than e to the minus s, into the minus the entropy. So the process is suppressed exponentially, but there is a decent chance that it happens. It's not too suppressed. So it seems that it is a possibility. Basically, the whole point of this check was to make sure that I'm not getting something much less than e to the minus s. In which case we wouldn't trust the semi-classical approximation. Now, okay, so the final thing that I should say a few words about is that this setup required to have a wormhole to begin with. So this nucleation happened inside this wormhole, and one should ask, how do we produce this wormhole to begin with? And there are two scenarios: one old scenario, and then a more recent one. The old scenario is to basically have a Schwinger pair production of these charged black holes inside, say, an electric or magnetic field. There is a more recent scenario proposed by these authors, which relies on the back reaction of the matter fields, and it produces or they are talking about a traversable wormhole. It's not totally clear what is the time scale for producing this traversable wormhole, but there is a chance, there is a hope that this traversable wormhole can be produced even faster than exponential time. And then once this, but in any case, once this traversable wormhole, if this traversable wormhole is available, then it won't be hard to get back to the setup that we are interested in. So going from traversable to non-traversable is always easy. We can just put some mass in and then ask what is the chances that those masses or that extra excitation decay into a bubble of the seed in that region. Okay, so to conclude, I talked about the uptunneling to the seeder as a way to explore what happened before the inflation, what is the scenario for the initial condition of our universe. The solution that I was talking about suggests that it is a possibility to quantum mechanically nucleate this false vacuum bubble. It is important that this bubble that we are producing is behind the horizon of a black hole, so it is it's not possible to directly send the signal after the bubble nucleates. It's not possible to directly send the signal from the outside to inside or vice versa. And finally, it would be interesting to explore holographically what would be, whether we can learn something about the seeder using this setup. Okay, thank you.
So maybe we can unmute ourselves and clap for Mehrdad. Okay, questions. Perhaps I can start. Mehrdad, in a situation in which, if you can produce this in an ADS CFT setup, would you say that the physics of what's happening inside the de Sitter space is part of the Hilbert space of the field theory, or is it somehow outside that?
I would say it is inside, but I would say it is, so this last point, that last hope, is probably not an easy one, because it seems that it seems to be as hard as understanding what's happening behind the horizon of a black hole holographically. I would say this this has a similar situation.
I see. But I was wondering. Sorry, I'm sorry, but I was wondering more generally. Is there a limit to the size of the de Sitter? You know, it sounds like if you produce a bigger and bigger de Sitter, you're producing a universe with very, very many degrees of freedom. It sounds unintuitive that that is contained inside a field theory with a fixed number of degrees of freedom. Somehow.
Yeah, it is very confusing, but I think it's related to the confusion about the de Sitter entropy. You could, I mean, I don't know the answer. I agree that it's a weird situation, but you could ask, for instance, if you want to take seriously the Gibbons-Hawking entropy, that's some finite number determined by the horizon size of the Sitter, but you can produce an exponentially big universe.
Right.
But yeah, I mean, that's an interesting question. I don't know.
Sorry, Loga, were you asking something?
Hello, no, Shiraz, sorry.
No. Okay. I thought somebody was asking when I. Sorry.
Yeah, Shiraz, I wanted to ask a question. Yeah, or maybe just some thoughts. So if you look at this Maldacena-Kurkulu model, the end of the world brane in some sense represents the, degrees of freedom of the left SYK model. You have an eternal black hole and you have the SYK model on two sides. And in some sense, this brane simulates some degrees of freedom of the other SYK model, which is behind the on the left side. And yeah, so now if you start analyzing this type of model in terms of low energy physics, then as you very well know, there is a very nice potential model actually that you can come up with involving the dilatation degree of freedom of the SYK model and also the JT gravity, the dilatation, the reparameterization invariance group parameter f of t, So as you remember, Maldacena-Kurkulu write it as the time derivative of that is the exponential of some Liouville type of field, and you have a very nice Hamiltonian system that describes how to sort of interpolate between black holes and no black holes, etc., etc. I was just thinking that if you turn on certain types, I mean, I can imagine turning on operators in the SYK model in which you have this type of potential scenario. A potential model can be created which may have this type of bubble nucleation possibility.
Oh, I
just
see.
wanted to make that point actually, yes, because ultimately, yeah.
Yeah, I should say yeah, I guess this is something I should study more carefully, because I'm not very familiar with the details of that paper. But okay. Yeah, this seems interesting.
Okay. Thank you.
Thank you.
More questions?
Sorry, one thing maybe related to Shiraz's question that I can mention is that or something that I said about the similarity with what happens behind the horizon of a black hole is that here it seems that it's a little bit better than behind the horizon because we can have well-defined TS observables. While it's a bit harder to talk about defining observables behind the horizon.
Sorry, this is probably off topic from your talk, but as you say, you know, these de Sitter spaces are sort of similar to these bags of gold behind horizons. And what do people what is the normal wisdom about these bags of gold? I mean, it's worded as a puzzle, right? That you can have very complicated states there, and how can it be part of the field theory entropy? And what is the normal? What do people normally say about that? What would?
Well, I think I'm not sure if there is some consensus about it, but I think it is related to this recent developments about the page curve and calculating black hole entropy, because you can also think about the fact that, for instance, in the case of the page curve, the entropy is increasing. You can consider these nice slices that are getting longer and longer in the interior of the black hole. So the naive picture is that this state behind the horizon is becoming more and more complicated, and therefore the entropy outside is increasing, keeps increasing. And now I think there is some way of understanding that this increases, this naive picture has to break down, and we have some more quantitative understanding of how it happens by shifting the saddle points that contribute to the entropy. So one can think that this is kind of analogous to that situation. Now, instead of having these longer and longer pieces of the spatial slice behind the horizon, we have these bags of gold, which are becoming more complicated.
Okay, thank you. Hey, other questions? Okay, if not, let's thank Mehrdad again for a very nice and thought-provoking talk. Thanks a lot, Mehrdad. I wish you could have been here with us in TIFR, but next time.
Thank you very much.
Yes.
Have a good rest of the day.
Thank you very much.
Yes.
Bye.